differential equations for undergraduate students. Today's topic is solution of Dirichlet problem. We are discussing about three-dimensional Laplace equation. We had seen that if our boundary conditions are given on cylindrical surfaces or spherical surfaces, we could change our problem from the Cartesian coordinates to the cylindrical coordinates or spherical coordinates. In the last lecture, we have changed our problem, that is the three-dimensional Laplace equation, into spherical coordinates, and we had seen that if our boundary condition is given on this sphere of radius r, this S, and then we had changed our Laplace equation into spherical coordinates as del by del r of r square del u by del r plus 1 upon sin phi del over del phi sin phi del u over del phi plus 1 upon sin square phi u theta theta is equal to 0. Now, if the boundary condition on this, that is the Dirichlet problem, says is the boundary condition is defined on the boundary, that is the sphere S only. If the boundary condition defined on this sphere S is independent of theta, that is, let us say if it is u r theta phi is equal to f phi, which is independent of theta, then we do expect that the solution of this boundary, this equation would be also independent of theta. If that is independent of theta, that is, it would not be u r theta phi, but only u r phi. That says is that the term u theta theta would be 0. So, we will change our partial differential equation as del by del r of r square del u over del r plus 1 upon sin phi del over del phi sin phi del u over del phi is equal to 0, with boundary condition as u r theta phi is equal to f phi, and as r is this point r, that is r is approaching to infinity, u r phi is approaching to 0. We have called this problem, that is this partial differential equation with this boundary condition and this initial condition, you could say, or boundary condition. We have got that this is called the Dirichlet problem. Today we will learn how to solve this Dirichlet problem in spherical coordinates. So, let us see is, that is, move to the solution of Dirichlet problem. We do have the partial differential equation in r and phi. The boundary condition is given on a sphere of the radius r, u r theta phi is equal to f phi, which is independent of theta. So, we do expect the solution to be, and another condition is u r phi is approaching to 0 as r is approaching to infinity. So, we will take the solution of this using the separation of variables or the product method. Since we are saying is that the solution would be depending upon r and phi only. So, we will take the u r phi as the product of two functions g r and h phi. Then the partial derivative of u with respect to r would turn out to be the simple ordinary derivative of g with respect to r and h as a constant, there it would remain as such, and partial derivative of phi would turn out to be the ordinary derivative of h and g r remaining as same. So, now if I take the first partial derivative with respect to r, we would get dg upon dr times h phi. The second derivative with respect to r, partial derivative of u, we would get d2g over dr2 into h phi. Similarly, for phi we would get gr multiplied with dh over d phi and gr multiplied with d2h over d phi 2. So, now if I substitute these derivatives in this equation and divide it by gh, that is u r phi. So, let us first write this equation in more simpler form, as it would be r square del 2 u over del r 2 plus 2 r times del u over del r plus del by del phi sin phi, that is it would be 1 upon sin phi cancel it out, and we will get del 2 u over del phi 2 plus cot phi, the derivative of sin phi is cos phi. So, cos phi upon sin phi cot phi times del u over del phi is equal to 0. Now, substitute del 2 u over del r 2 del u over del r from this u r is equal to g r into h phi. We would get r square g double dash, because what we would be getting is del 2 u over del r 2 as g double dash r, that is the derivative of g with respect to r into h phi. Now, we are dividing it by g into h. So, we would be getting it g double dash upon g plus 2r g dash by g, that is where this g double dash and g dash means they are derivative of the g r with respect to r, the second derivative and the first derivative. Then here we would get it h double dash upon h, and here we would get cot phi times h dash upon h, that we are taking on the right hand side. So, we do get it r square g double dash upon g plus 2 r times g dash upon g is equal to minus of h double dash upon h plus cot phi times h dash upon h. Of course, this g is function of r only and h is the function of phi only, and here also we are having the coefficients also as r and phi, the r function of phi only. So, we do get this left hand side is a function of r and the right hand side is a function of phi. So, if they are remaining to be equal, if according to this equation, that says is they must be equal to some constant, say k. Now, equating these two, we do get as usual method we have done in many partial differential equations, that we do get two ordinary differential equation. One is from here r square g double dash plus 2 r g dash minus k g, that is g we are taking this side, and the other one would be h double dash plus cot phi h dash plus k h. So, we are getting two ordinary differential equations, r square g double dash plus 2 r g dash minus k g is equal to 0 and h double dash cot phi h dash plus k h is equal to 0. Now, see the first equation. Here the unknown variable is that variable is r and the unknown function is g. So, this is equation which is in g and r. If you do try to remember, we are getting is this equation where the second order linear equation where the coefficients are r to the power r square and r so on. So, this is we do know this famous Euler-Cauchy equation. Now, the solution of this equation would be simpler if I take this constant k to be of a special form. So, let us say k is n into n plus 1. Then what this equation will become? This equation will become r square g double dash plus 2 r g dash minus n into n plus 1 times g is equal to 0. We do know that if you have to remember it, that is we have done this Euler-Cauchy equation. The solution of this equation are assumed to be of the form r to the power m. So, we take the solution of the form r to the power m, that says is g dash would be m times r to the power m minus 1 and g double dash would be m into m minus 1 times r to the power m minus 2. If I substitute this, that is if this is a solution, they must satisfy this equation. So, if I substitute this in this given equation, what we would get it? Simply m into m minus 1 times r to the power m minus 2 into r square, that is r to the power m, plus 2 times m into r to the power m, again r and r to the power m minus 1, minus n times n plus 1 r to the power m is equal to 0. Since r to the power m we are saying is a solution, so it will not be 0 for all r. So, what we say is that the coefficient, that is r to the power m, if I do take common, the coefficient must be equal to 0, and that gives me auxiliary equation. What would be that coefficient? M square minus m plus 2m minus n square minus n, that is we would be getting is m square plus m minus n square plus n. So, making it more simplified form, the auxiliary equation is coming out as m minus n times m plus n plus 1 is equal to 0. The roots of this auxiliary equation from here is very clear, that is one would be n, another root would be minus n minus 1. So, these are the roots of this auxiliary equation. That says is now we are getting the two solutions of this second order ordinary differential equation, which is Euler-Cauchy equation. One is as given as r to the power n and another would be r to the power minus n minus 1, r 1 upon r to the power n plus 1. Now, we are using two different solutions. We are taking one solution as denoting it as g n r, another as g n star r. Here n is arbitrary. What we have taken? We have taken this n to be, this k to be a special form as n into n plus 1, where n we are taking as integer. So, that we are getting it as a solution in a nice form. That is how we are doing it. So, we have got the two solutions for this first equation. Now, let us move to the second equation. Since we have got the solution of the first equation taking k as n into n plus 1, we will move to the second equation in the same manner, taking k is equal to. So, we will take k is equal to n into n plus 1. Now, this equation is in phi and we are having a coefficient as cot phi. What we would actually make the change of variable over here, that is rather than phi, now we would use another variable w, which is cos phi. So, what we say is that h of phi would be changing it to say some other function h of cos of phi. So, we would take it, that is function h of cos of phi. In that, if I change it, so here the derivative h dash with respect to w with respect to phi, we have to change it to with respect to w. So, we will go with the our chain rule. So, dh over d phi we could write as dh over dw into dw over d phi. From here dw over d phi would be minus sin phi. So, what we get it minus sin phi dh over dw. Similarly, if I go for the second derivative d2h over d phi 2, this is nothing but d by d phi of dh over d phi. dh over d phi is minus sin phi dh over dw. So, let us first differentiate it with respect to phi using the product rule. So, the derivative of minus sin phi is minus cos phi. So, we do get minus cos phi dh upon dw minus sin phi times the derivative of dh upon dw with respect to phi. Now, for this we will use the chain rule. So, the first term is as such. For the second term we would be getting is d by dh of dh by dw, that is d2 h over dw2 into dw over d phi. dw over d phi is minus sin phi. So, we will multiply it, we get plus sin square phi d2h over dw2. Now, substitute this d2h over d phi 2 and dh over d phi in this given equation. So, we change this equation in the variable phi to variable w. We do get minus cos phi dh over dw plus sin square phi d2h over dw2 plus cot phi times h dash, that is minus sin phi cot phi dh over dw plus k is n into n plus 1 times h is equal to 0. Now, you see equation we have to get in h and w, we have to remove the terms of phi. Cot phi into sin phi, cot phi is nothing but cosine phi divided by sin phi. So, we would get it here cosine phi. So, we will get minus 2 times cosine phi. Cosine phi we are saying is w. So, if cosine phi is w, then sin square phi is nothing but 1 minus w square. So, let us rewrite this equation in h and w only. Sin square phi would be writing as 1 minus w square d2h over dw2 minus 2 cosine phi would be w minus 2w times dh over dw plus n into n plus 1 times h is equal to 0. Now, let us see this equation also we do recognize. This we had already done, this is a famous Legendre equation, where we are having is 1, if you do remember that there we have done it 1 minus x square y double dash minus 2 x y dash plus n plus into n plus 1 times y is equal to 0, where n has to be integer. So, now we will treat n as integer. We do know the solution of this Legendre equation is nothing but the Legendre polynomial p n w. Now, w we are saying is cosine phi. So, we will write p n cos phi. So, what we have got ultimately the solution for our partial differential equation u r phi, which is g phi into h phi, g r into h phi, we do get this Legendre polynomial. If you do remember, that is for your remembrance, I am rewriting it over here. It is summation m running from 0 to capital M. Capital M has to be either n by 2, or you could say is the integer value of n by 2. That is, if n is even, it would be simply n by 2, if n is odd, it would be n minus 1 by 2. From minus 1 to the power m into factorial 2n minus 2m upon 2 to the power n factorial m factorial n minus m into factorial n minus 2m into w to the power n minus 2m. You see, this is a polynomial of degree n. We had when m is equal to 0, the degree would be n. When m is n by 2 or n minus 1 by 2, we would be getting it running over there, that is the degree, that power of w would be 0. So, this is a polynomial of degree n. So, the solution finally we have got the solution of the Laplace equation as GNR into Hn cos phi, which is Hn cos phi is actually Pn cos phi. So, we have got UNR phi as An times r to the power n Pn cos phi, where I am using the first solution GNR as r to the power n, and for that we are using the coefficient arbitrary constant An. Now, because we do not for the Legendre polynomial the arbitrary constant we already choose as 1. So, we do choose it here as A n, or we can say another solution if I use instead of G n, if I do use G n star, I would get let us say another solution u n star r phi as B n upon r to the power n plus 1 times P n cos phi. So, we have got now two solutions for our Laplace equation. So, now we have to find out the solution of Dirichlet problem, that is we have to satisfy the boundary condition. Boundary condition says is u r phi is f of phi at r is equal to capital R, a fixed radius. Now, we see is that is here this solution u n or u n star, they are depending upon an arbitrary integer n. So, to get that satisfy the boundary condition, we would use this Fourier method for solving Dirichlet problem using the boundary condition. So, we will use the solution of Laplace equation by Fourier method. The boundary condition first we have been given is u r theta phi is equal to f phi. Now, since if you do remember we are talking about that is our boundary is a surface of the sphere. Surface of the sphere that says is that we have to find out, we have got that Dirichlet problem in the last lecture we have got that it is a example is that is calculation of potential or the temperature inside the boundary and outside the boundary. So, let us first talk about the inside the boundary, that is what we are calling interior problem. So, let us first find out the solution of interior problem, that is we will get u r phi at all those r which are inside the sphere or that r is less than or equal to capital R. For that case we would use our solution from the first solution u on r phi. Since my Laplace equation is again a second order linear equation, homogeneous equation, we can use the principle of superposition principle, and that is fundamental result, and we can have our solution as summation n is running from 0 to infinity u n r phi, where u n r phi is nothing but a n times r to the power n into P n cos phi. So, we have got is that let us say the solution is u r phi is n is equal to 0 to infinity a n r to the power n P n cos phi. Now, for this we would satisfy our this boundary condition. This solution we are saying is that is for r less than or equal to r. So, boundary condition means at r is equal to r, if I write it out this solution that this r has to change to this capital R, this is a fixed value, the radius of the sphere, n is running from 0 to infinity a n r to the power n P n cos phi, this must be equal to f phi. Now, what it says is we have to find out this a n, this constants such that this is satisfied. What is this? What we are saying is this function f phi is represented by an infinite series, where this infinite series is actually consisting of, this is a constant, this is a fixed value r to the power n P n cos phi. P n cos phi, this is the Legendre polynomial, that is what we are having polynomials of degree n. So, as n is varying we would be having polynomials in cos to the power n, or again we are getting is Fourier kind of polynomial. So, what we are calling, they are Fourier series, of course we would get the series in the terms of cosine terms, powers of cosine phi, but we have those special form, that is rather than having only as the powers of cos and sine, we are having them as P n cos phi, that is the Legendre polynomial in cos phi. This we would call Legendre Fourier series. This has been a little bit you could obtain if you just say is that is, since my in the Legendre polynomials you have done that Legendre polynomials are orthogonal, that says is in this way the representation can be done. If you do remember that in Sturm Liouville problems we have done, that is those eigen functions were orthogonal, then we can present any function in the series form of the orthogonal functions. So, in that manner we could actually represent it, and using those kind of results, here I would not go in the detail, I would simply say is that is a n times r to the power n from here can be given as the coefficient 2 n plus 1 upon 2. So, this r to the power n from here I am taking this one, integral 0, actually this is orthogonal on the minus 1 to plus 1. If you do remember, that is p n w. So, I could say is integral minus 1 to plus 1 p n w into f dash w. F dash w, what we are saying is f phi, if I change my variable from phi to cosine phi as w. So, let us say is that function f phi can be given as f dash of w, then f dash of w p n w d w integral minus 1 to plus 1, that should be ideally my coefficient. Now, since w is we are taking as cosine phi, so if I change the variable, my dw would change to minus sine phi cosine phi, and the range, that is the limit, minus 1 to plus 1. Minus 1 will take phi, that is w as minus 1 will take phi as pi, and w as plus 1 will take phi as 0, and since minus sine phi d phi, that we would be getting as dw, using the properties of definite integral, we could write it as 2 n plus 1 upon 2 to the power 2 into r to the power n integral 0 to pi f phi p n cos phi sin phi d phi. So, what we have got? We have got the solution of the interior problem r u r phi at for all r less than or equal to r, that inside the boundary, as a series summation n is running from 0 to infinity a n r to the power n p n cos phi, where a n is being given by 2 n plus 1 upon 2 into r to the power n into integral 0 to pi f phi p n cos phi sin phi d phi, where f phi is actually the boundary condition which is independent of theta. Now, we see from here, if my r is greater than r, or if I take r approaching to infinity, certainly this will never approach to 0, because we would be we are having is r to the power n, and n is an integer which is greater than 0. So, this will never approach to 0, that is the condition. The another boundary condition which says is u r phi is approaching to 0 as r is approaching to infinity cannot be obtained from this solution. That is, if r is greater than or equal to r, outside the boundary, that is outside the sphere, this cannot be treated as a solution. So, that problem, that is getting the solution u r phi at all the points which are outside the sphere, that we would call exterior problem, and for that this solution will not work. So, let us see the solution of exterior problem. Let u r phi is now another solution we are taking. If you do remember, the g n star we are taking 1 upon r to the power n plus 1. So, there we would get, if r is approaching to infinity, that 1 upon r or 1 upon r to the power n would approach to 0. So, we will take this g n star, that is, now we are assuming our solution u r phi as taking summation n is running from 0 to infinity b n upon r to the power n plus 1 p n cos phi. Now, satisfy the boundary condition that at r is equal to capital R, that is at the this one, the boundary condition if we do satisfy. So, this solution we are taking for r greater than or equal to r. Now, the boundary condition is that r is equal to r, u capital R theta phi should be f phi. Try to satisfy this boundary condition for this solution, we do get it as 0 to infinity b n upon capital R to the power n plus 1 p n cos phi is equal to f phi. That is, again we are getting f as a series of Fourier Legendre series, you could say. So, again using the similar manner, we could get b n upon r to the power n plus 1 as integral minus 1 to plus 1 p n w d w and f p n w into f dash w d w, where my w is cosine phi, and the constant we would get 2 n plus 1 upon 2. So, again changing it in the similar manner in the phi, we do get 2n plus 1 upon 2 into r to the power n plus 1, because now we would be getting bn upon r to the power n plus 1. So, this would go this side into r to the power n plus 1 integral 0 to pi f phi p n cos phi sin phi d phi. So, we have got this solution for all n 0, 1, 2 and so on. We have got now the solution of the exterior problem, that is you could say potential at all the points which are outside the boundary, that is outside the sphere. We do get it as bn upon r to the power n plus 1 p n cos phi, where bn is being given by this constant as 2n plus 1 upon 2 r to the power n plus 1 integral 0 to pi f phi p n cos phi sin phi d phi, where f phi is nothing but the boundary condition, that is the function which has been given as the boundary condition. Now, let us see one example, that is how this thing can be applied. Find the potential inside and outside a spherical capacitor consisting of two metallic hemispheres of 1 feet radius, separated by a small slit for insulation, if the upper hemisphere is kept at 110 volts and the lower is grounded. So, now we have to find out the potential inside and outside the spherical capacitor, while we have been given the temperature has been kept at this volts has been kept as 110 volts, and in the upper hemisphere and the lower hemisphere we have been it has been grounded. So, let us see in the figure, that is how this boundary condition would look like. This says is there is a sphere. So, this upper sphere is at the 110 volts and the lower sphere we are having is it is 0, and there is a slit between these two spheres. Now, what this it says simply that because our boundary condition is given on the surface of the sphere. So, we can and we have to find out the potential inside and outside the sphere, that is we have to solve the interior problem as well as the exterior problem. We have to find out any point x y z inside this sphere and what is potential at that point, and any point outside this sphere what is the potential over there. So, this we do know that this potential problem is nothing but 3-dimensional Laplace equation with the boundary conditions. We do know that since my boundary conditions are being given on the or the boundary is given as a surface of the sphere, we would move to the spherical coordinates. If we are moving to the spherical coordinates, just see reminding that is what we mean by spherical coordinates. These x, y, z are our Cartesian coordinates. If we are moving to this spherical coordinates, then we do have r is that the distance from the origin to any point, whether it is inside or outside, wherever this any point in this space, that is we are having is that is r, and theta is the angle which we would say is in this is in the xy plane, that is whatever the cross section this circle it is making, this is theta. So, if I take r is running from -1 to +1, that is the minus r to plus r or -1 to +1, because here the radius is being taken as 1 feet. So, it should be 0 to 1 here and -1 to +1, and theta is over here. Then we see is that this phi we would be saying is that is to be going only for this sphere as 0 to pi. So, for hemisphere we would get this phi is from 0 to pi by 2 only, and for the another hemisphere we would have that is the upper hemisphere 0 to pi by 2, and the lower hemisphere phi would range from pi by 2 to pi. What it says is that my boundary condition which is been given, that is upper hemisphere is kept at 110 volts and the lower is grounded, that says is now my boundary condition is not depending on theta. We would be getting is it is a constant for phi ranging from 0 to pi by 2, and it is another constant from pi by 2 to pi. So, we can very well assume that our boundary condition is free of theta. So, we could say is u r theta phi is f of phi, and then the solution we would assume is that would be also independent of theta, that is we could move to the problem just now we had solved. So, first we will change the problem, that is 3-dimensional Laplace equation, into a spherical one. As usual we have done it, del upon del r, r square del u upon del r plus 1 upon sin phi del upon del phi sin phi del u over del phi plus 1 upon sin square phi u theta, theta is equal to 0. Since the boundary condition is given on this sphere, as we have just now seen, is that says is that it should be independent of theta, it should depend only on phi. So, we say is that boundary condition is u r theta phi is equal to f phi, which is the function is been given as 110 for the phi ranging from 0 to pi by 2 and 0 for pi by 2 to pi. That says is my solution would be independent of theta, that says u theta would be 0. So, we will come back to the equation r square d 2 u over dr 2 plus 2 r times du over dr plus del 2 u upon del phi 2 plus cot phi times del u over del phi is equal to 0, with the boundary condition u r theta phi is equal to f phi, which has been given by this function 110 at phi ranging from 0 to pi by 2 and 0 for phi ranging from pi by 2 to pi. And this would lead to the other condition we would be requiring is that is the potential outside this one. So, if r is very far away, certainly u r phi must be 0. So, we say is that the other condition we would assume as so we will come to the our Dirichlet problem, del upon del r square del u over del r plus 1 upon sin phi del over del phi sin phi del u over del phi is equal to 0, with u 1 comma theta comma phi as 110 for phi ranging 0 to pi by 2 and 0 for phi ranging from pi by 2 to pi, and u r phi is approaching to 0 as r is approaching to infinity. So, this is our known Dirichlet problem, for which just now we had got the solution. The solution we have got as the 2, that is, since here also in this example we have to find it out inside the sphere and outside the sphere. So, inside the sphere, so solution of interior problem we had find it out was u r phi summation n is running from 0 to infinity a n r to the power n p n cos phi, where a n was decided by the boundary condition and the constant was defined as 2 n plus 1 upon 2 to the power 2 into r to the power n integral 0 to pi f phi p n cos phi sin phi d phi. Now, here f phi is nothing but this constant between the range 0 to pi by 2 and 0 in the range 0 pi by 2 to pi. So, for evaluation of this a n we would have to evaluate the integral from 0 to pi by 2 only. So, let us first evaluate this integral a n. 2 n plus 1 upon 2 r was 1. So, r to the power n would vanish, it would come as 1. Function f phi is constant in the range 0 to pi by 2, that is f phi is 110. Integral is now 0 to pi by 2. Since 110 is constant, we are taking it outside the integral sign, p n cos phi sin phi d phi. Now, let us move to this, what is p n cos phi? We would evaluate this integral 0 to pi by 2 p n cos phi sin phi d phi. Again we will assume cos phi as w. So, minus sin phi d phi would be d w, and at 0 the cos 0 would be 1 and cos pi by 2 is 0. So, we would get it 0 to 1. So, again in that manner we would write all these things, and p n w we would, if you do remember, we have got this polynomial of n degree, if m is running from 0 to m, this summation minus 1 to the power m factorial 2 n minus 2 m upon 2 to the power n factorial n minus m factorial n minus 2 m into w to the power n minus 2 m. So, now we will substitute p n w, instead of p n w we would substitute this one, and instead of phi we would change the variable to w. So, the range is 1 to 0, and since it is minus sin phi, so we would get 0 to 1, and what we would be getting now 2 n plus 1 100 by 110 by 2, that is 55. So, 55 into 2 n plus 1. We are again making is that the summation sign and the integral sign can be interchanged, that is we could say is that the this interchange is possible if we say the series is uniform convergence and all those things. So, we are assuming all those niceties of the mathematics are being holding true over here. So, we can make it out. So, summation m is running from 0 to capital M minus 1 to the power m. All these are constants. So, we can take outside the integral sign factorial 2n minus 2m upon 2 to the power n factorial m factorial n minus m factorial n minus 2m integral 0 to 1 w to the power n minus 2m dw. Now, this integral would be certainly w to the power n minus 2m plus 1 upon n minus 2m plus 1, which is evaluated from 0 to 1 will result only 1 upon n minus 2m plus 1. So, if I am adding it 1 upon n minus 2m plus 1, that will add it n minus 2m into n minus 2m plus 1, we would simply say it would be factorial n minus 2m plus 1. So, finally, what if I substitute these things, what I would get? A n I would be getting is as 55 into 2n plus 1 as such. Summation m is running from 0 to capital N means is the integral value consisting in n by 2 minus 1 to the power m 2n minus 2m factorial upon 2 to the power n factorial m factorial n minus m factorial n minus 2m plus 1. This is the constant a n we have got. Now, for n is equal to 0, 1, 2 and so on, this is what is our constant. So, let us try to find out certain values. If I take n is equal to 0, n is equal to 0 says is that is capital M will also come out to be 0, that is the summation is only on the single value when m is equal to 0. M is equal to 0 means is here n is 0. So, this is factorial 0. Factorial 0 we do know is that we take it as 1, 2 to the power 0 is 1, this is 0, this is 0, this is 1. So, what we do get it simply here 1, n is 0. So, here also, so we will get simply a naught as 55. Similarly, if I go for n is equal to 1, n is equal to 1 means is 1 is odd number. So, this m will not go till 0, that is again we would be having only single point at m is equal to 0. Here n is equal to 1. So, it would give me 3 into 55, and what we will get from here? Here we would be getting is this minus 1 to the power 0, that will give me 1. Here 2 n minus 2m, m is 0, n is 1. So, it is factorial 2. Here it is 2. So, factorial 2 is 2, 2 upon 2, then this is 0, this is factorial 1, this is factorial 1, this would be factorial 1 plus 1 2. So, what we would be getting it 1 by 2. So, we would get finally it as 165 by 2 or 82.5, because 55 into 3 would be 165 upon 2. So, 85.2. Similarly, if I go for n is equal to 2, then we have two terms 0 and 1, and we would get the coefficient from both the places. You just calculate it, you would get it as 2 minus 2 actually. So, a 2 would be 0. Similarly, for a 3 if I do go, I will again get the two terms, m is corresponding m is equal to 0 and m is equal to 1. Again calculate all these, putting this n is equal to 3 and m is 0 and 1, that is this sum of the two terms. Or finally, we would get like that we can calculate these coefficients. So, finally, what will be the solution, that is what is the potential inside the sphere? U r phi is n is equal to 0 to infinity a n r to the power n p n cos phi. Now, a n just now we had calculated as for some values. So, let us just try to write it out. 55, that was the a naught, r to the power 0, that is 1, p naught cos phi. If you do remember Legendre polynomial, p naught x is 1, whatever be the x. So, we would get 55. Then p 1 cos phi, that is cos phi actually, you could find it out using those ones. So, this is 82.5 times p 1 cos phi minus 48.125 p 2 times cos phi and so on. Now, from those functions Legendre polynomials you had already done, you have done, that is what is p n x, p 1 x, p 2 x, p 3 x, p 4 x, like that you had already calculated. You can very easily write this series in the terms of cos phi or the powers of cos phi, and from there what we do have to, we can calculate the potential at any point. How? The series sum. Series sum certainly is not going to be very easy to find it out unless until we do know what is the convergence and particularly what will be actually this particular series sum. But certainly using certain functions, that is nth partial sum, that is for some functions for some n as 5, 6 or something, we could find out, we can approximate the potential at that point, at any particular point r. Now move to the potential at outside the sphere, that is solution of exterior problem. We do remember that we had find out the solution of exterior problem not using this n into r to the power n, but bn upon r to the power n plus 1. So, for that the solution was n is running from 0 to infinity, bn upon r to the power n plus 1 bn cos phi. Here bn, if you do remember, we were having 2n plus 1 upon 2 r to the power n plus 1 0 to pi f phi pn cos phi sin phi d phi. Now r is, in our given problem, the radius is 1 feet, that is r is 1. So, what I would get is 2n plus 1 upon 2 times integral 0 to pi f phi pn cos phi sin phi d phi, that is same as our an, because why? F phi is your constant in the range 0 to pi by 2 and 0 in the range pi by 2 to pi. So, what we do get is 2n plus 1 upon 2 into 110 0 to pi by 2 pn cos phi sin phi d phi, this is same as an. So, in this our particular problem, what we have got, that bn and an are coming as same. Just now we had calculated that a naught as 55, a1 as 82.5, a2 as it should be p3, a2 as 0, a3 as minus 48 point something. So, we do get now the solution outside the sphere, that is exterior problem. B naught is same as a naught. So, what we are getting is bn upon r to the power n. So, r to the power n plus 1. So, we would get 55 upon r plus a1 we have got as 165 by 2 upon r square p1 cos phi minus 385 upon 8 r cube p3 cos phi and so on. So, what we have got finally, actually we have to solve, we have to get the potential inside the sphere and outside the sphere. What we have got, for the inside we have got this series, for outside we have got this series. Using this Legendre polynomials, p1x is x, p2x is x square minus and so on, p3x is x cube and all those terms, we can find out the approximate values at different points r over here, and then we can get the approximate solutions. You can check, that is with the some as we have done in many our solutions, that is we have took the in the Fourier series also we have done is, that is calculated the partial sums for n is equal to 3, 4, 5 and so on. So, you can try here with the n is equal to say 5, that is you take the first term, second term, this third term, because the a2 is 0. So, this would be a3 and so on. You could go till for first 6 terms and you can check for different values of r. First thing is, you could check very easily for, if I take r is equal to capital R, that is 1 itself, my both these solutions would match, that is at the boundary r is equal to 1, both these solution would match, and there you could check that it would actually approximate our boundary condition. And for different values, that is when r is less than 1, we have to use this solution, for r greater than 1 we have to use this solution. So, here r has to also come. So, we do get that different solutions, that is potential inside and outside. So, today we had learned, that is how to solve the Dirichlet problem when the boundary condition is given on a sphere. Similarly, if the boundary condition is given on the cylinder, we can change our problem to the cylindrical problem, and there using the boundary condition, whether it is depending upon z or not and all those things, we have to either we can change it to the two variables, that is r theta and z, either we change it to the r and theta or we change to theta and z, and accordingly we can use again the product method, that is the method of separation of variable, and we can go ahead with the solution. So, the method for solving this partial differential equation, that is 3-dimensional Laplace equation, first we are trying to see is, that is where the boundary condition is being given. If the boundary condition is given on some known surfaces, that is as a cylinder or the sphere, we will try to change our problem to the spherical coordinates or cylindrical coordinates. If the boundary is given on the cubes or this cuboids, we could move to the directly to the Cartesian coordinates itself we could solve. We could use this problem, we could solve this using this product method. So, this spherical and cylindrical coordinates we have taken because of its practical applicability in many engineering problems. So, we have learned how to solve the 3-dimensional Laplace equation. So, that is all for this today's lecture. Thank you.